Existence and uniqueness of quotient and remainder. Whenever a positive integer a is divided by lesser positive integer b, there is a unique quotient with a unique remainder which is less than b. First of all, we prove the existence. We have already assumed b is less than a. So we can always write a equals to 1 times b plus open bracket a minus b close the bracket. So there's always a quotient which is q equals to 1 and the remainder which is r equals to a minus b. And a equals to q times b plus r is valid. For the ease of further proof, we write it as a equals to k1 times b plus r1. If the first remainder r1 is larger than b, say when 22 is divided by 5, we may have the first remainder, which is 17, larger than 5. Then we further divide the first remainder r1 by b again, and get r1 equals to k2 times b plus r2. And note that k2 times b, which is an integer, so it is not less than 1. For example, the first remainder, which is 17, when divided by 5, we may have the second remainder, which is 12. So we substitute this into the previous expression and get a equals to open bracket k1 plus k2 close the bracket times b plus r2. For example, 22 equals to 2 times 5 plus 12 in our case. And note that r1 minus 1 is not less than r2. Now the second remainder may still be larger than b. In such a case, we further divide the second remainder, r2, by b again, and get r2 equals to k3 times b plus r3. For example, if the second remainder is 12, we divide it by 5 and get 12 equals to 1 times 5 plus 7. And 7 could be the third remainder, r3. We substitute this into the previous expression and get a equals to open bracket k1 plus k2 plus k3 close the bracket times b plus r3. So 22 equals to 3 times 5 plus 7. And note that r1 minus 2 is not less than r2 minus 1, which is not less than r3. We keep going on the process until we get to a point when b is less than rm. Rm is the mth remainder. Then we further divide rm by b again and get rm equals to k of m plus 1 times b plus r of m plus 1. For example, the nth remainder may be 7, which is still larger than 5. Then we may get 7 equals to 1 times 5 plus 2. We substitute this into the previous expression again. And get the remainder equals to r of m plus 1. For example, 22 equals to 4 times 5 plus 2. R of m plus 1 is 2. And note again, r1 minus m is not less than rm minus 1, which is not less than r of m plus 1. If we put m equals to r1 minus b, then we get b is not less than r of m plus 1. So there are two cases. First, if b equals to r of m plus 1, then the remainder is 0. If b is larger than r of m plus 1, then we keep r of m plus 1 to be the remainder. So in any case, we still have a equals to q b plus r, and the remainder r is less than b. So the existence of a quotient and the remainder is proved, with the remainder less than b. Next, we prove the uniqueness. If there are two different quotients, q and t, and two different remainders, r and s, we subtract the first equation from the second one and get b times open bracket t minus q close the bracket equals to r minus s. Now, suppose the two quotients q and t are different, and we can assume t is the larger one. Since t minus q is positive, so r minus s must be larger than b. But we already have r less than b in the previous proof. So this is contradictory. So, according to reductio ad absurdum, the remainder r must be unique. Since the remainder is unique, the quotient q equals to open bracket a minus r close the bracket divided by 5 is also unique. So the proof is done.